For the last time, hello and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy. In this video, we'll learn how to find the Bayesian Nash equilibrium of the first price sealed bid auction. This method can also be used to find the Bayesian Nash equilibrium of the all pay sealed bid auction. We'll describe the first price sealed bid auction and find its Bayesian Nash equilibrium. Note that this auction is not the same as the first price sealed bid auction with two allowable bids that appeared in the problem set. In this auction, we allow any non-negative bid. In the first price sealed bid auction of this video, each bidder submits a sealed non-negative bid. The seller opens all of the bids and awards the object to the highest bidder, and the highest bidder pays her bid to the seller. Let's give two examples of how this auction might proceed. In this example, bidders 1, 2, and 3 bid 0, 2, and 4 respectively. Bidder 3's bid is the highest, so she wins and pays her bid, 4. In this example, bidders 1, 2, and 3 bid 0, 4, and 4 respectively. In the event of a tie, a winner is selected at random from the tied highest bidders. Suppose the tie breaks in favor of bidder 3. She wins and pays her bid, 4. We'll suppose that valuations are uniformly distributed on the 0-1 interval and find the Bayesian Nash equilibrium of this game. The type spaces and action spaces are both continuous, so we'll introduce our third and final method for finding the Bayesian Nash equilibrium, equating the direct and indirect expected utility functions and solving this expression for the Bayesian Nash equilibrium strategy. In the case of an auction, the Bayesian Nash equilibrium strategy is a bidding function. In the list of steps below, the first step is finding the direct utility function, the second is finding the indirect utility function, and the third is equating the two and solving for the Bayesian Nash equilibrium bidding function. A bidder receives her valuation less her bid when she wins, and 0 otherwise. Therefore, her expected Bayesian Nash equilibrium payoff is the probability that she wins multiplied by her payoff less her bid. A player wins when her bid is the highest, so in order to make sense of this expression, we need to determine the probability of that event. We'll make two important assumptions during this exercise, the first of which is the monotonicity assumption stated here. The equilibrium bidding strategy is increasing in a player's type. This assumption lets us relate a player's type to the probability of winning the auction. If bids and types increase together, the probability of having the highest bid is exactly the probability of having the highest type. Capital F of Vn is the probability that bidder n's type is higher than the type of any one other bidder. Since there are n-1 other bidders, the probability that Vn is the highest of all the types is capital F of Vn to the n-1st power. The problem states that types are uniformly distributed on the 0-1 interval, so capital F of Vn is Vn itself. We can write bidder n's expected Bayesian Nash equilibrium payoff as shown. Now we'll turn our attention to step 2, writing down the indirect utility function. Both the direct and indirect utility functions represent bidder n's expected payoff in Bayesian Nash equilibrium. The only difference is how we construct the two. We'll start by considering the following function, which represents a bidder's expected payoff when her type is Vn, but she represents herself as type Wn. Now, a bidder can't actually change her type. If she wins, the object is worth Vn to her no matter what type she represents. What does it mean to represent oneself as type Wn? It means to bid B of Wn, the bid associated to the represented type. Representing oneself as type Wn means to bid B of Wn, and that one wins with probability capital F of Wn to the n-1st power, written here as Wn to the n-1, since types are uniformly distributed on the 0-1 interval. We could replace Wn with Vn and obtain again the direct utility function from step 1, but that won't help us towards our goal of finding the bidding function. We now come to incentive compatibility, the second important assumption about the structure of the Bayesian Nash equilibrium bidding function. Nothing in the rules of the auction requires that a bidder bid according to her true type, and the private nature of this information means that such a rule would be utterly unenforceable. The only thing that can compel a bidder to represent herself truthfully is her own self-interest. Incentive compatibility is the assumption that a bidder maximizes her expected utility by representing herself truthfully, i.e. bidding B of Vn. The incentive compatibility assumption lines up neatly with the envelope theorem. The envelope theorem relates single and partial derivatives along the path of a function's maximum. The left-hand side tells us to substitute Vn for Wn and differentiate the resulting function with respect to Vn. We can't compute that derivative directly because we do not know the functional form of the bidding function. But the envelope theorem tells us how to compute that derivative indirectly. The right-hand side tells us to take the partial derivative of little pi with respect to Vn, and then substitute Vn for Wn, and that we can do so since the bidding function in pi of Wn Vn depends only on Wn. So, incentive compatibility assumption made, we'll differentiate using the envelope theorem. Here again is the conclusion of the envelope theorem that we'll use to differentiate little pi of Vn. Wn to the n-1 is a constant with respect to Vn, so leave it alone. The derivative of Vn minus b of Wn with respect to Vn is 1. Evaluating at Wn equals Vn gives Vn to the n-1. The derivative of little pi of Vn is Vn to the n-1. Now, this expression is useful because it is the derivative of the indirect utility function. We can recover a function from its derivative using the fundamental theorem of calculus. Here is the integral. In addition to integrating, we need to determine big pi of 0, the initial condition. Big pi of 0 must be 0, since a bidder with Vn equals 0 should bid 0 in Bayesian Nash equilibrium. She certainly shouldn't bid a positive number, since if she wins, she will receive negative payoff. She can't bid a negative number. Therefore, she should bid 0 and guarantee herself a payoff of 0. Now, integrate. Evaluate from 0 to Vn, and done. Here are the direct and indirect utility functions. Again, each expression represents the same quantity, bidder n's expected payoff in Bayesian Nash equilibrium. The direct versus indirect distinction refers to how we constructed them. Now we're ready for the last step, solving for the bidding function itself by equating the direct and indirect utility functions we found in steps 1 and 2. Here they are together. Divide by Vn to the n-1. We aren't dividing by 0. Vn equals 0 is a probability 0 event, so all is well. It's fine if you stop here, but it's somewhat more traditional in the case of the uniform distribution to use this expression. For the sake of completeness, here are all the steps and their results. Thanks so much for watching this video about how to find the Bayesian Nash equilibrium of the first price sealed bid auction. Congratulations, you made it. Fair winds and following seas.